In this video, we are going to look at Rolle's theorem and the mean value theorem. Let's first look at Rolle's theorem. So Rolle's theorem says, let f be continuous, so we have to have a continuous function on a closed interval from a to b, and let f be differentiable on the open interval from a to b. If the function value at a is the same as the function value at b, then Rolle's theorem holds, and it guarantees there is at least one number c in the open interval where the derivative at c is equal to 0. And so if we have some function, and here at a, and our function value at b, our function value at a and at b are exactly the same. Right? So that's what this part tells us. It's continuous on a closed interval, so continuous means we should be able to draw this picture without lifting up our writing utensil. Being differentiable tells us something about the smoothness, and so we're not going to have sharp edges. So it's going to be smooth from A to B. Then no matter what picture you draw here, we are guaranteed that somewhere in this interval there is a number c where that derivative is 0. Now here we actually have more than one number c. So we actually have 3 different locations where our derivative is equal to 0. Now, Rolle's theorem just guarantees there's at least one. We could have more than one. That's Rolle's theorem. Our second theorem that we want to look at here is similar to Rolle's, but it is more generic. It is much more general than Rolle's theorem, and that is the mean value theorem. So the mean value theorem, just like Rolle's theorem, requires for us to have f being continuous on a closed interval, needs to be differentiable on an open interval. But we don't have to have equivalence at the two endpoints. If we have this, then we are guaranteed there is a number in the open interval where f prime of c is equal to this. Now, what is this? F of b minus f of a over b minus a. That is really just the slope between the two endpoints. So we are guaranteed to have the derivative at somewhere on the interior being equal to the slope between the two endpoints. Let's draw another graph. So if this is A and this is B, maybe we have f of A right here, f of B is maybe up here. Then if I were to draw a graph, so maybe my graph looks like that, then we are guaranteed that the slope between those two lines shows up as a derivative somewhere on the interior. So let's say right there-ish, maybe not quite there. So maybe right about there, there's a point where the derivative, the slope at that point, it matches the slope between the two endpoints. It looks like there's another spot, maybe right here. Now, we're not guaranteed there's more than one. We just know that there's at least one spot where the derivative at that point is the slope between the two endpoints. All right, so that is the mean value theorem and Rolle's theorem. So with those two things, this mean value theorem is actually what would allow a police officer to give you a ticket if they knew when you got on a turnpike and they knew the time that you got off the turnpike. They could find your average speed, right? So they can find your average speed on that turnpike. And if your average speed is above the speed limit, then they know that you for sure had to hit a speed above the speed limit somewhere on that interior. Now, if you have a lawyer and things, then maybe they can prevent that from actually going through. But that is the argument. That is a perfectly legitimate mathematical argument. Now, assuming that you have a continuous differentiable function. So if you have a non-differentiable function, non-continuous function, then maybe somehow there's a way that you start here, and then you have this gap, and all of a sudden you're up here, and you don't hit this speed. That's the stuff of science fiction. All right, in our next video, we will look at some examples where we prove the existence of these values C. We will see you there.